It's a question that has fascinated scientists and philosophers for generations. Until recently, the dominant view held that life's basic building blocks, amino acids, sugars, nucleotides, emerged through chemical processes on early Earth. But a new astronomical discovery is turning that idea on its head. Deep in the constellation of Orion, a young protostar known as V883 Ori has offered a stunning glimpse into the cosmic origins of life's ingredients, and what scientists have found could profoundly change our understanding of not just how life began on Earth, but how widespread it might be across the universe. V883 Ori lies approximately 1,300 light-years from Earth. It's what astronomers call a protostar, an infant star still in the process of forming. At this stage, stars are surrounded by massive rotating disks of gas and dust known as protoplanetary disks. These are the raw nurseries of planets, comets, and other celestial bodies. But they're not just physical construction zones. These disks are also chemical laboratories, where simple elements combine into more complex compounds. Understanding what molecules exist in these disks and how they survive the violent birth of a star has been one of the great challenges of modern astrochemistry. Protostars like V883 Ori often undergo intense growth spurts, known as episodic accretion outbursts. During these periods, the star suddenly gobbles up large amounts of gas and dust, radiating energy and heating its surrounding disk. Normally, much of a protoplanetary disk remains extremely cold, so cold that molecules freeze into ice and are nearly undetectable. But during one of these bursts, the disk warms up dramatically, and previously frozen molecules vaporize into gas. This rare event gives scientists a precious opportunity to study the chemistry of a disk in detail using advanced instruments like ALMA, the Atacama Large Millimeter sub-millimeter array located high in the Chilean Andes. What scientists found in the V883 Ori's disk was remarkable. They detected several complex organic molecules, or COMs, which are considered key intermediates between simple space chemistry and the biochemistry of life. These included molecules such as acetaldehyde, methylformate, and most intriguingly, formamide. Formamide is a molecule of particular interest because it can lead to the formation of both amino acids and nucleic acid bases under the right conditions. In other words, it's a molecule that sits on the cusp between non-living chemistry and the precursors to life itself. What makes this discovery groundbreaking is not just that these complex molecules exist in space. We've known that for years. The real significance is that these molecules appear to survive the chaotic and destructive process of star formation. Scientists once feared that the intense radiation and high-energy winds during a protostar's formation would essentially reset the surrounding chemistry, breaking down these fragile molecules and forcing them to reform later under different conditions. But the findings from V883 Ori suggest otherwise. These organic molecules can endure through the violence. They don't just survive, they are passed down, inherited by the very disks that go on to form planets. This revelation bridges a crucial gap in our understanding of the origin of life. If complex organics like formamide and methylformate are present in protoplanetary disks before planets even form, then Earth, and likely many other planets, may have been born preloaded with the molecular raw materials needed for life. It suggests that the chemistry of life doesn't start on the planet. It starts in interstellar clouds, continues in star-forming regions, and is delivered to planets via cometary or meteoritic material during the early stages of planetary development. Evidence for this hypothesis is not limited to distant protostars. Organic molecules, including amino acids, have been found in meteorites like the famous Murchison meteorite that landed in Australia in 1969. NASA's Stardust mission even found glycine, an amino acid, on particles collected from the coma of comet Wild 2. These discoveries support the theory of panspermia, the idea that the ingredients for life might be distributed throughout the cosmos, transported by comets, meteors, and interstellar dust. But what makes the V883 Ori discovery uniquely important is the setting. This isn't just finding amino acids on an old meteorite that collided with Earth. This is detecting complex life-related chemistry in the very birthplace of a planetary system in conditions similar to those from which our own solar system emerged 4.6 billion years ago. It means that complex organics are not just relics from space, they are actively integrated into the planetary formation process. So what does this mean for the possibility of life beyond Earth? If protoplanetary disks across the galaxy commonly contain these same complex organic molecules, then the chemical foundation for life may be widespread. In recent years, astronomers have discovered thousands of exoplanets. Some orbit within the habitable zones of their stars, and some resemble Earth in size and composition. If they too inherited molecules like formamide or acetaldehyde during their formation, then the chances of life developing, even simple microbial life, go up dramatically. This shifts the conversation from "is life possible elsewhere?" to "how common is it?" The V883 Ori study supports the idea that life is not a rare cosmic accident, but the likely outcome of a universal chemical heritage. It supports a view of the cosmos in which biology is built into the very structure of planetary systems. Where planets form, the seeds of life may already be sown. Of course, there are still many unknowns. Organic molecules alone do not guarantee life. The leap from chemistry to biology, from molecules to metabolism, from formamide to functioning cells, is vast. But the more we learn about the chemical processes in star-forming regions, the more we realize that life might not be the exceptional case. It might be the expected outcome. As telescopes like the James Webb Space Telescope continue to peer into the depths of star-forming clouds and examine the atmospheres of distant exoplanets, discoveries like the one at V883 Ori will serve as critical guideposts. They remind us that the universe is not just a physical realm of rocks and radiation. It is also a deeply chemical universe, rich with potential. And perhaps a biological one. So the next time you look up at the night sky, remember, the molecules in your DNA might not have started here on Earth. They could have been forged in the cold darkness of interstellar space, born in the heart of a collapsing cloud, and delivered to our planet in the earliest moments of its formation. Life on Earth may not be a miracle, it might be a cosmic legacy.